What if black holes create new universes? An area of space known as a black hole is one where light cannot escape due to the strength of gravity there. Because stuff has been compressed into a small area, gravity is extremely powerful. An aging star may experience this. Black holes are invisible to humans because no light can escape them. They are undetectable. Can black holes transport you to another world? Is there a different universe in the black hole? Or what if black holes create a new universe? To know the answers to all these questions, continue watching the video till the end. For more interesting content like this, subscribe to our channel, Salty Space. Hit the bell icon to receive notifications whenever a new video is posted. Black holes are among the universe's most powerfully destructive forces. In magnetism, opposites do indeed attract, but when it comes to black holes, the ideas of creation and annihilation aren't typically congruent. The question is, what if something extremely large was produced by black holes? A novel theory that does the following has been put forth by a group of scientists. It's possible that black holes create a singularity with a very high density in addition to warping space and time. A recent study published on a preprint service suggests that they may also cause a continuous transition between the inside of a black hole and the beginning of a new universe. In other words, the research raises the possibility that black holes could truly delve into a certain type of multidimensional object known as a brane, giving birth to an entirely new universe in a subsequent massive Big Bang. This hypothesis, however, is based on string theory, a set of theories that seeks to unify all natural forces. As a result, the possibility is very remote. However, the concept alone draws attention to the fascinating mystery that the unknown inner workings of a black hole give to us. We can still attempt to approach a black hole using mathematics, barring the creation of a miraculous spacecraft that can transport us across its event horizon while still alive. The fabric of space-time curves away from the plane at a singularity as predicted by Einstein's vacuum field equations for gravity. The curvature of black holes also goes far beyond what we would anticipate from the gravitational fields that normally surround stars or planets. It is a region where the principles of classical physics, which date back to Sir Isaac Newton's day, start to fall apart. However, the study claims that this breakdown in classical physics also takes place during the Great Bang when the cosmos is forming. A few hundred years later, quantum physicists sought to figure out how to incorporate Einstein's theory of gravity into a quantum framework. Black holes and Big Bangs are examples of singularities, therefore any attempt to unify all physical theories under quantum physics would also need to account for them. The goal of the most recent study is to achieve this. By adding a single object to the effective field and theory description of space-time and matter, the researchers suggested a method for concurrently resolving black holes and cosmic singularities. The 20th century was full of shocks in terms of our knowledge of the universe. We used to believe that the Milky Way galaxy was the only place in the universe where we could view the stars and other celestial objects. We used to believe that Newton's law of universal gravitation, which governs the universe, was static, unchanging, and possibly everlasting. In just a few short years, all of that drastically changed. Newton's gravitation was surpassed by Einstein's general relativity, which revealed the connection between matter and energy and the structure of space-time. His equations implied that the universe couldn't be static and had to be evolving throughout time, which the discovery of the expanding universe proved to be the case. Additionally, his hypothesis foresaw the existence of black holes, which were eventually identified, detected, and even directly imaged. This gave rise to the crazy but still hypothetical hypothesis that perhaps the universe originated in a black hole. An event horizon is what distinguishes a black hole from other objects. It is a boundary that tells a vastly different tale to objects inside than outside of it. Any object outside of a black hole's event horizon will feel its gravitational effects because the black hole's presence will bend space, but it can still escape. It won't definitely fall into the black hole if it accelerates or moves quickly enough in the right direction, but it might escape its gravitational pull. The core singularity of the black hole will instantly swallow any object that passes over to the other side of the event horizon. An infalling object will arrive at the singularity within seconds of crossing the event horizon because of how severely the spacetime inside a black hole is bent, adding to the mass of the black hole. The event horizon gives the impression that the black hole is forming, gaining mass, and expanding over time to observers outside of it. We can see up to around 46 billion light-years away in all directions at the outer limits of what our detectors can detect. E equals mc squared, Einstein's most well-known equation, may be used to calculate an equivalent mass for the entire observable universe, if all the energy from all of these forms is added up over the entire observable universe. There is also something astonishing that occurs when you examine the equations that control a black hole. You will discover that your distance lowercase r extends from capital R, the Schwarzschild radius, to infinity if you begin just beyond the event horizon and leave the black hole. The same distance lowercase r instead goes from capital R, the Schwarzschild radius, to 0. On the other hand, if you begin just within the event horizon and measure your progress from the black hole to the core singularity, you will discover that lowercase r is equal to 0. This is significant because from capital R to 0, all the properties of space outside a black hole's event horizon are equal to all the properties of space inside the black hole's event horizon. This is true at all points in both directions. The black hole's interior and exterior are mathematically equivalent if you just replace the distance lowercase r with its reciprocal 1 over lowercase r. Or more precisely, if you replace all instances of lowercase r over capital R with capital R over lowercase r. The laws of physics physically break down in a black hole's singularity, making it impossible for us to predict what will occur there. However, we can predict what will occur along the event horizon's edge. The information is encoded by the event horizon as matter enters the black hole. Together, the black hole and event horizon expand until the surface area is precisely the proper size to hold all matter that has ever entered the black hole since its creation. Everything in our cosmos might be explained by all of that knowledge. Believe it or not, the math also resolves several long-standing problems as it adds up. In 2014, researchers from the Perimeter Institute and the University of Waterloo originally suggested this idea. The Perimeter Institute claims that one significant issue with the Big Bang is that the theory postulates that a singularity created a cosmos that is comparatively uniform, predictable, and understandable. It seems improbable. The black hole hypothesis is much simpler, albeit extremely difficult to visualize. It's possible that we reside in a universe that is contained within a black hole. Black holes might be all that is present below.